Welcome back to a partially cloudy day in Thailand. The rain is holding off, and we have version 2 of the circuit board, which I am now cleverly calling DC-VC-CB. Stands for DC, voltage and current on CANBus. Now let me walk you through some of the version 2 changes, and then I'll take you over to the board. So the first thing we did is we updated the package layout for the current sensing chip. Alert viewers will remember that it's got two giant rectangular tabs that did not have a slot cut through the board for them, so I had to drill it out by hand. I worked closely with the guys in England that define the package layouts, and I went back and forth with them a couple of times, but I finally had to go and manually add the slot definition as needed specifically for Design Spark, because their packages are layout independent, layout software independent, and they couldn't go to the next level and define the slot the way I needed it to be defined within Design Spark. So I'll show you what I had to do for that. I worked with them to update the USB chips package. This guy right here had to go through a couple of revisions because it turns out that this chip comes in three different three different capabilities: maximum, normal, and minimum. I needed the minimum one, and the minimum one uses a different package layout and a different pinout from the other two. So they simply copied and pasted 3 times, but they actually needed to physically change the package I was using. And that's why I couldn't get USB to work on my board at all, because the physical layout was just not right. That has all been corrected. I fixed a problem on the original board with the labeling of my input and output terminals for the current sensor. So all my current values were coming in negative. I added a blinky LED right here. Just for fun, it's always good to have something that blinks so that you know you at least have some control over your circuit. And for version 2, the major functional improvement was adding voltage sensing. So to do that, I needed to add both input and output terminals for the positive wire in the circuit, and input and output terminals for the negative wire in the circuit. And then also to perform the voltage sensing, I used a resistor divider network, a top divider and a bottom divider. The voltage difference between the two is read by a differential analog input signal into the MCU. So there's some microprocessor magic that happens right here to read the values. In order to handle different levels of voltage with good accuracy, you want to scale the input voltage from whatever it is, 20 volts, 50 volts, 400 volts. You want to use these two resistors to scale the voltage across these two analog pins to just below 5 volts. So for my situation, for my 84 volt battery pack, R5 wants to be 10 megohms and R3 wants to be 510 k ohms. That presents the proper voltage across these pins as high as it can without blowing out the chip, and also provides a high resistance value so that very little current actually flows through this to perform the voltage reading. Okay, what else did I do? I updated the reset push button because my estimation of the package and its pinout while it was in the mail from China was not correct. That has been fixed. I added header pins to select the voltage or the power source that the board is going to work from. You can either put a header pin across here, in which case the board will be powered from the USB connector, or you can put a pin here, in which case the board will be powered from 12 volts and regulated down to 5 volts. This jumper is obviously for use when it's in your vehicle. This jumper is used for when you are updating firmware, or you're basically working with your computer and over the USB bus. You do not want to have both of these connected at the same time, because bad things will happen, and I'm not going to try and protect you from your stupidity by adding a lot of extra components here. On the board, I've labeled the USB chip. I added this table here for the resistor and capacitor codes, because I was constantly having to go back and forth and to a website and look up these codes as they come out of those parts reels. They just have these tiny little codes on them, so that'll be helpful in the future. I changed one of the resistors from, I believe, 300 ohms to 360 ohms because it's a much more common resistor value. On the board itself, I added the voltage capability to the board. I updated the full screen to say it's version 2.0. And I also added, on the board, I added a non-plated slot between the plus and the minus terminals, and I'll show you that in a second. I also, on the board, I added a link to the documentation on the silk screen. So let's go over and take a look at how the board turned out. Okay, here's the updated board. You can see it's grown a little bit in height. I just wanted to give a little more breathing room, and I also grew it far this way because we now have a minus part of the circuit with a mounting terminal here, another mounting terminal here. You can see this is a straight pass-through, but it's needed because to measure voltage, I need to sample what's flowing through on the plus wire and what's flowing through on the minus wire. So you just screw down your wire here on your ground, you screw down your wire here. You can see we have the negative terminal comes into that resistor divider network right here, R3 and R5. Scaled down the input voltage into the MCU, so that's all happening here. Here's the positive input, and we pick up the negative input over here. Not a lot has really changed on the rest of the board. I kind of gave some things some breathing room. I added the blinky LED here. I added a place to mark the voltage maximum, which is defined by R3 and R5. The amps maximum is defined by the particular ACS 770 family part that you solder in here. I changed the part name, and I also added this documentation that points to a bit.ly served link, which actually points to my Blogspot blog, and I've added an essentially empty blog article here that will define the documentation for the board. I restructured and updated the package for the USB chip and rewired it. If you're eagle-eyed, you will see that the package is definitely different than version 1. I also added the 2 power headers. Here's the one where you put a little jumper across here, and the board will be powered by 5 volts from the USB pin. And if you put the jumper right here, the board will be powered by 12 volts coming from the vehicle, which then flows through the regulator circuit. Other than that, everything is pretty much the same, so we should be ready to go. Now, I just want to talk about those slots for a minute, because the slots are now defined for the current sensor, and you can see it looks like there's only a hole here, but if we take away everything except the mechanical layer, you can see there's a physical slot defined here, and also a giant slot defined here, which is meant to act as a physical separation between the plus of the circuit under test and the minus of the circuit under test. Physical slots are good. It's probably overkill. I could have just left some space, but I figured just for safety, I would put that slot in. Also got to learn how to do slots, so that's always a good thing. And then I'm going to generate the manufacturing plots. which will include this mechanical layer, which JLC PCB wants in something called an outline plot. So that should help them understand that's how I want the slot cut. And then I'll upload the files, and then in a couple of weeks I'll have my boards back in my hand. Hopefully less than 2 weeks. Would I get them in about 8 days last time? So cross your fingers. And here's the projected view of the final board. You can see our positive and negative terminals with the big slot in the middle, although the board doesn't know how to deal with that. We have our new blinky LED. We have a new USB chip outline. We've got the 2 jumpers for power, which actually got rendered correctly here and here. And I changed the font. It's a much more readable font for the labeling. So let's upload the board. Okay, the file has been uploaded, and curiously, the cost of the board started out at $2, but then when I uploaded my board, the price jumped to $9, and then it said there's an actual cost for a per board basis, and for 10 boards, it was $4.08. So that's 40.8 cents per board rather than the 20 cents a board I had before. Now it is slightly larger, and I don't know, maybe that spilled over into a different panel size for them or something. But now, so the total cost went from $2 to $11.04 for 5 boards. So I selected down to 5 boards for $2.04. So the $9 base charge plus $2.04 for 5 boards, plus $4.81 for shipping, which actually went down. It was $5.55 before. So I'm getting 5 boards for $15.85, which is a little over $3 a board, where before it was about 75 cents per board. But that's okay. It's still freaking cheap. Now today is a Saturday, and they say they're closed for 2 days for the Dragon Boat Festival. So I guess it'll go into production on Monday, although it says in production, but I think that just means it's been accepted into their system. And I should see the boards probably the middle to the end of next week. As you stare out on my beach, I would ask you to subscribe to my channel and click like on this video so YouTube thinks I'm worthy again, and I have so many people on my channel that they'll give me 10 cents a day in ad revenue. So I thank you for that.